Okay, so hopefully you didn't find the first exercise where you had to log in and play around with the server too complicated. I think everyone did relatively well. There were a couple of snags, of course. As always, if there seems like there's something that doesn't work, ask me about it. Yeah, I know that you can't directly copy out of public HTML into another folder if you are using relative addresses or relative paths to that folder, because public HTML is actually a link to a folder that is not in your user space. So if you do that, then it's going to give you an error, a access error. And so ask me about that. That was actually part of the assignment, to ask you about that and get it right. Also, additionally, I don't know if anyone in here did this or not, but there were a couple of people who accessed your files on the server via a FTP client. So what you did was you signed in via FTP, you downloaded, you created a file on your own computer, saved it the way you wanted it, and then uploaded it to the server. That's not what I wanted you to do. It's not what I told you to do. I wanted you to, through the terminal, access those files and update them. Okay, so that was the whole point of the exercise. I think that was about it, though. Did anyone have any questions before we get started? Okay, cool. So today we are moving on to chapter 2. Chapter 2 from the Xi book, anyway. And in particular, this week we're looking at sections 2.1 through 2.3, I think. It's either 2.2 or 2.3. Yeah, 2.3. And the topic of that material really boils down to processes. Okay. The chapter goes on to talk about threads and some other things, but this is an introduction to processes, right? So here is an overall of the process concept. Okay? It is an abstraction of a running program. An abstraction of a running program. And there's that term again that keeps popping up whenever we talk about, well, computers, but also operating systems. This is an abstraction, right? Everything with computers and in computer science is just abstractions on top of abstractions. This particular abstraction is meant to embody everything we need to know, okay, about processes. So literally everything that the operating system does hinges on the idea of how you implement processes in that operating system, the details of what information about each running program you keep track of, where you keep track of it, okay? They encapsulate resources for the running programs. They tell us about which program is currently being run, right? In sum, they make the computer seem like it can do more than one program at a time. We've mentioned this a couple of times in previous lectures, right? The operating system, one of its main goals is as a resource manager. The process allows us to encapsulate what resources for each program when running, we need to keep track of in order to keep things so that they can run on the machine, okay? So yeah, there is the bookkeeping aspect of this, but more importantly, there is the persistence aspect of processes, okay? Processes are persistent and they last even though they will not always be actively executed, okay? What I mean by that is they have to be swapped in and out, because only one process can run at a time. Only one instruction can be handled at a time. So it only makes sense to have the process, the resources, the instructions for that program that's currently running. Those are the ones you want to be stored in your active RAM at any given time. But they are going to be swapped out, moved to the side, so that other processes running other programs can come in. And this is not a slow process, right? The swapping processes might happen on the scale of tens or hundreds, if we're lucky, of milliseconds. So every 100 milliseconds or so, right, or maybe even tens of milliseconds. Oh yeah, thanks. Every tens of milliseconds or hundreds of milliseconds or so, we've got to, so in active RAM, okay, we've got to swap out one process, okay, and swap in all the information about another process, and then start executing this process. And this process may not be finished. And this process may not have just started. Okay? The process one that we just swapped out, it's not necessarily done, okay? And process two, which we're swapping in, it might have been swapped out previously before it finished, okay? So when we do this, at the very least, when we swap out processes, we need to remember what operation we were executing, what instruction we were executing when we swapped them out. And if we need to remember what instruction we were executing when we swapped them out, then we need to remember all of the resources that were allocated to each of these. We need to be able to swap in and out the set of instructions that makes up the program, okay? And we need to do this in such a way that it is transparent from the perspective of the process that itself, or the program, or the application, however, whatever level you want to think about it, okay? When you write a program, when anyone writes a program, okay, they can never guess ahead of time when they're going to be swapped in and when they're going to be swapped out. There are no set points at which the programmer decides, my program is going to be swapped out here, and it's not going to be swapped out before here. No, that never happens, okay? From the programmer's and from the user's perspective, okay, it is as if that program was running the entire time, okay? And likewise, is just as much as similar to, is just as much like that all the other programs were running at the same time, okay? Even though behind the scenes at the level of the operating system, they're being swapped out like mad, okay? Back and forth, 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 okay? Because only one process can exist in RAM, in active memory at any given point, okay? So we won't have loaded the CPU with information from multiple processes, only one process. Okay? Does that make sense? So it should be clear to you that how this is implemented is one of the main things that defines what makes one operating system different from another operating system. Okay? At the ground level. Yeah? If you like Linux, you probably like Linux for reasons other than this, but what makes Linux different from Windows and Windows different from Mac OS X and so forth and so on is the way this architecture is built, okay? Well, amongst other things, like for instance, we know how Linux works, but unless you are at a high level at Microsoft, you don't know how Windows works, okay? And even there may not be anyone anymore who remembers exactly how how Windows works from top to bottom, okay? Right, but how this is implemented is critical. So again, we're not going to talk about very much. I do have some notes in here to tell you about some details that make a distinction between Unix/Linux, Windows, and we'll talk about that just briefly. But for the most part, we're not interested in talking about the nitty-gritty details of each operating system. We're more interested in discussing the overall general design and talking about the design decisions that have to go into how you build a system that can swap out processes. And the way that you do this is with a structure called a process control block, or a PCB for short. It is a data structure. It's a data structure that the OS uses to keep track of each process. Okay. It contains things like, but not necessarily limited to. Definitely it has to have the current instruction address. Okay? Because at this level, what we mean by program is we mean a set of instructions that can be executed by the processor. Right? That's what a program is. When you're writing a C++ program, you can think of all kinds of and use all kinds of abstractions that are supported by the syntax. But when the compiler is done, you've got a bunch of zeros and ones, okay? And those zeros and ones represent an operation code, an opcode, followed by some number potentially of parameters, okay? It might be the address to a specific cache. It might be some value that you want to store in a cache, but this is all binary, okay? That's what a program is. So the set of instructions that get executed and is something that needs to be kept track of when a program is running. And what do we call it when a program is running? A process, okay? Processes are programs when they are running and all the information about them, okay? So one thing we obviously need to keep track of is the current instruction address. Then we've got the call stack, okay? And your book refers to this as an execution stack. And I have to be honest, I've never heard it called an execution stack before, so I had to look that up to make sure that that's what that was. But yes, these are two different names for the same thing, call stack, or if you prefer, function call stack. That's actually a little bit higher level. A call stack and the execution stack. Okay, so back from your early days of programming, what's the call stack useful for? You guys remember? If you didn't have me, you might not have been told exactly. But I tend to make a point of telling my 155 classes what the call stack is, because it makes things make sense. What's the call stack? It's a stack of things that get called. So it's related to the heap. It's a different part of memory than the heap. Yeah, and so it's related to the heap because it's not the heap, it's the stack, right? So what is a stack, incidentally?
Certain things called up base and pop things off.
Okay, so it's a data structure that is a first in, last out data structure, okay? Or a last in, first out data structure. So you make a stack by, like, you've got a stack of things, you put the first thing on the bottom, you put something on top of it, you can only have access to the thing on top. Now, so this is a stack, like that. This is a, so let me dive in here, the call stack. So it's a stack, like this. Okay, tend to draw them like this. You push onto the stack, you pop off from the top of the stack. Oh yeah, thank you. Right? Okay. And it says, so that's the stack part. What's the call part? What are we calling? Yeah, that's actually true, but it's a group of instructions. So think as a programmer would think, and tell me what we're calling a function. Okay, so what we're calling are functions. When we call a function, does the function that we were running before keep on executing? Right, it's underneath. It's wait. It waits for the called function to return. So what we do when we create a function is we create a activation record. Okay, an activation record. And in this activation record, we remember the return address, and we have the list of all the local variables. Okay, and the reason why this comes up in early programming, like 155, 255, is because when the function ends, so this gets pushed on, like we call foo, and so foo's activation record gets pushed onto the call stack, right? Which means we now have an address of what we were doing before foo got called, and the value and locations, we know the location now, of all the local variables that got declared inside foo, including any parameters that were passed by value, okay? And so when foo, the function, finishes, this gets deleted and removed from the stack, or gets popped from the stack. So what happened to all the local variables? Well, if they were dynamic memory, then they would have been on the heap. Okay? And so we would have to delete them. But let's assume these are all just regular variables. Automatic variables is what they call them in C++. Auto local variables. They get deleted. And that's why the scope works the way that it does, right? Because these things get popped off the call stack, they get deleted, they're no longer there. And so when you're not inside this function, not only do you not have access to those variables, but their values are gone. And so the next time you call this function, you get a whole new copy of the same variables with the same name, but different values, stored potentially in different places. All of this happens really inside process control block. Okay? All that needs to be taken care of in some fashion. So you got the call stack in there. Then you need a list of resources that have been allocated to this process. Every time, y'all got to throw something at me. You need a list of resources. So what I wrote was this. Okay. So you need a list of resources that have been allocated to that process. And then you need the program itself. That is to say, the list of instructions. Okay? So however you've saved the list of instructions, sometimes that address should reference the specific instruction that needs to be executed next. Okay? All right, I see squinty eyes and confused looks, so let me clear things up for you. You'll ask me a question and I'll try and clear it up. Either that or I'll make it worse, but you know, if we say nothing, there's no chance. Any questions? Okay, so I'm going to drill down and talk a little bit more about how these are often structured. And again, if the way that processes are swapped in and out makes an operating system, then that's why this requirement, dang it, this requirement, swapping things in and out, this requirement is what drives this design, okay? So whatever the requirements are for your operating system that you need to meet, you're gonna design your process control blocks in such a way that you can meet those requirements, right? Swapping in and out things, okay? Doing it efficiently, right? So this process control blocks is how you meet these requirements, okay? And others, like we don't want to take up a lot of space. We don't want to have a lot of space wasted in RAM, okay? We want to have efficient lookup times for the resources and for the instructions, and we want to be able to efficiently use the function call stack. Okay? So I'm going to drill down on that just a little bit. But before we move away from the abstraction that you are perhaps most comfortable with, that would be the program. Okay? In computer science, we benefit and suffer from the idea that computer science is the same thing as programming. Okay? It is not. Programming, the act of programming, is a tool that computer scientists use to meet their objectives. Okay? And it's a tool that's multifaceted and takes some amount of time to master. Okay? But you're familiar with computer science through the abstraction of the program, the set of instructions, and the order in which they need to be executed. Okay? So how is a program different from a process? Okay? So programs and processes are not the same thing. Programs are the list of instructions. You break it right down, the list of instructions, and you know stuff is rolled in there like control structures, okay, decisions, variables, both static and dynamic. Okay, all of that is boiled into, all that gets boiled down though into a set of machine code instructions that will be executed given certain circumstances. Okay? A process is what you get when you run or when you execute a program. Okay? To drive this point home, we usually think of every running program as having a one-to-one relationship, the program and the process that you get when you run that program, okay? But this is actually not necessarily true. What you actually have is you have a one-to-many relationship, okay? If you start this program, every time you run this program, you get a new process, okay? So here's my first time that I ran my program, and here's my second time that I ran my program, and I get a different process, okay? This should not blow your mind, right? If I open up multiple windows here, can I even, will it let me? Yeah. This is the same program running twice, okay? This program is called File Explorer, right? It has a graphical user interface, but that really doesn't matter. Behind the scenes, it's just zeros and ones, okay? And it lets me see what's on this, what files and folders are in the folder tree for this computer. This has its own process. This has its own process. So that when this iteration of the running program is active, whatever happens over here, oh boy, what do I do? Okay, go away. Doesn't affect what's happening over here. Okay? So every time you run the same program, you get a new process. All right, does that make sense? It gets its own copy of where it is in the instructions and its own function call stack, and maybe its own copy of the program itself, but maybe not. Okay, Because sometimes what clever operating systems will do is that they will allow they will sacrifice a certain amount of memory to put the instructions in memory, and then they'll have pointers that are associated with each process that both point to that same shared space. Okay, so that you don't have to copy the entire program, all the instructions, to two different places and take up a lot of extra memory. That's a thing that makes sense, right? It's going to save you memory to do it that way. The other thing about programs and processes is that I said it's one program leads to many processes. And I said that because I said every time you run the program, you might have multiple processes. But in fact, it's one level deeper than that, because programs can be divided into multiple processes, each of which calculates a different thing. Okay? Now, this is a thing that you have to be careful about, right? Because if there is shared memory between multiple processes that are both part of the same program, then you have to synchronize access to that memory, right? Is this a concept you've come across before? How many of you have taken database? One or two, okay? So when you're doing transactions with a database, right, you have to be certain that if two programs are using the same database, and one needs to write to a location and the other needs to read that location that this guy just wrote, that this guy doesn't go first, okay? And so there are some complicating factors with that. Can you enforce that the second guy doesn't go before the first guy? Well, yes and no. No, because remember, no process is guaranteed any amount, any percentage, or any specific instruction to be executed before it gets swapped off the processor, okay? So at any time, any process can go from running to waiting, and likewise from waiting to running, and in any order, okay? So this problem leads us to something we're not going to talk about today, which we will talk about later: synchronization. And how do we make multiple processes synchronize with each other? Okay, that's going to be a major topic as we move on. All right, but that is not what I want to talk about today. So let's just put that on the back burner. All right, any questions about the difference between programs and processes? You can design a program so that it uses multiple processes consecutively. And by consecutively, I mean consecutively in the same sense that programs can run consecutively, right? They appear to run consecutively. They can be swapped in and out. You don't get one process every time. You don't get only one process for every program. Every time you run a program, you get a new process, okay? So you can have one program sitting there, and every time you run it, you get a new process. So you get M or more, some number of processes, each of which is separate, okay? Any questions about that before we go on? All right. So this is the part where I said I was going to tell you about Windows and Unix-like systems. And of course, each one of these distros, if you will, is different. So like included in this, I mean BSD, which is one branch of Unix, open source branch of Unix. I mean Linux and all its multiple distros. Okay, and I also mean Mac OS, because at the bottom, Mac OS is based on BSD. Okay, how do these two systems, these two major systems, if we divide them like this, handle creating processes? Okay. So in Windows, there is a system function called create process. Okay? All one word, capital C, capital P. There are actually a bunch of overloaded versions of that function depending on what you want to do. Okay? They're all called create process, and they all take different numbers and different types and different order of types of parameters. This sucks. This is terrible. Mostly because it tries to do too much. It both creates a process and loads the process. And so since it's trying to do both of those things in one system call, you'll have sometimes 10 or more parameters, right, that you have to type in. And what I mean by that is when you're writing code, you're writing like a C++ program, and you want that program to spawn a new process, like you use the create process statement and then like open parentheses, close parentheses, and you might have several lines of things to pass to create process. Okay? It's a real bear. I don't know, it might have gotten better since the last time I used it. Yeah, there it is. All right. Those are all of the parameters you have to pass when you want to use it this way. So good luck with that. All right. Now with Linux, it's easier, but well, I think it's easier. You might disagree. With Linux, Unix, the only instruction that creates a new process is the process called fork. Okay, fork. And what fork does is it spawns a new process with a copy of the instructions for the old process. In fact, not just the instructions, but the entire environment of the old process. It makes a copy of all that stuff. Okay, so what's the problem with that? If you create a new process and it has all the same instructions as the old process, including the next thing to run, the current instruction, what are you going to have? The same thing. It's going to run the same thing. So the standard question is, how do you get it? How do you get it to be different? We want a new process with new instructions, okay? And the answer is that there are ways to tell which process is the parent, and which process is the child. So you can program your code to check to see if it is the child, and if it is the child, there's an instruction called exec VE, which takes a couple of parameters, nothing like create process, to load new instructions in. Okay? To load new instructions in. And then both of those processes, from the operating system's perspective, they're related, but they keep getting intertwined. They go off on their own lives. Okay? Incidentally, this is how the shell works. Right? This is how the shell works. If I log in to the server, cs.csis.work, and I type in vim file name, okay, vim pops up, right? What happened was the shell spawned off, forked off a new process, and it forked that process in such a way that it was a copy of the shell, but the shell is instructed that, hey, if you're the child, run the program that we just received as a command line instruction. them, okay? And so boom, boom. The shell is a little bit different because it's programmed to wait on the children to finish, but there's no reason why that has to be the case, okay, just in general. Right? You got two processes running, and they, as far as the operating system is concerned, they have nothing to do with each other. Okay? We will get a chance to get our hands dirty with some of this in the next couple of weeks. Okay? I have plans for you. And that might send shivers down your spine, and maybe it should, but we'll get through it. We'll make it through. Any questions so far? Distinction between a process, how processes get spun up, anything like that? Processes and programs. Okay, so let's talk a little bit about transitioning between processes. And what I'm going to show you next is the fundamental finite state machine for all processes, regardless of what operating system you're using. Okay? There are three states: running. These are the three states, fundamental states, that a process can be in: running, ready, and blocked. Okay? If a program is running, that means that its memory, its address space, its stack, it is loaded in memory, in RAM, and the instructions are being executed. Okay, that's what running means. So how does a running program go from running to ready? Well, there's a transition here. Okay, running to ready. I'm going to come back to this transition in just a second. How does it go from running to blocked? Okay, well, those processes that are blocked are waiting on a resource. And resources could be any system resource, like you don't have a framework for knowing about semaphores and mutual exclusion and that kind of stuff, but there are system resources that have to be shared amongst the processes potentially, and if you're waiting on one of those, then you go to blocked, okay? But it also could be waiting on a device, okay? Or a human, right? If it's waiting on input, okay? It's waiting on a human, or if it's waiting on a device to do something, right? At human scale, moving the mouse seems to happen instantaneously, but this device takes time to register and return its values, okay? Printers are a great example. Printers take forever and a day in operating system speed to finish doing what they need to do, okay? Any device that you can think of, the drives, all the drives take forever to read in information, okay? They take forever. The processor is way faster. The bottleneck is always in writing out to the drive. So information can go out to the drive, to the hard drive, or to your solid state drives. Solid state drives are a little faster. Go out to your hard drive, and it'll take a while to spin to that part of the disk. And all that is happening self-contained on the disk, right? On the hardware on the disk. That stuff takes time. The time that takes could be used by other processes, okay? So if a running program starts to wait on something to happen, then it gets moved off of the running state onto the blocked state, okay? All of its stuff gets saved somewhere, okay? Somewhere in memory. Okay, we'll talk more again about where that is as the weeks go on. right? So a resource request will cause moving from running to blocked. There is no path from blocked to running. You can't go from blocked to running because something, as soon as you moved to blocked, something moved on from ready to running, okay? Because what ready means is that all I need, me, the process, is a chance. Just waiting my turn, okay? Everything's lined up. I'm ready to go. I know what the next instruction is. Everything, I'm waiting on nothing. I just need the processor to execute my instructions, okay? The goal is to maximize the CPU throughput. Always have the CPU executing something, okay? So if the process that the CPU is running gets blocked, move the blocked process to the blocked state where it will wait until it becomes unblocked, and move something off the ready state, which is ready to go right away, onto the running state and let the processor go again. Okay, does that make sense? There is a line. Once you're blocked, you're not blocked forever though. From blocked to ready, if the resource releases and you're waiting on it and you can claim that resource, then you go to the ready state. You do not go directly back to running, okay? Because something is running and processes cannot interrupt each other. Only the operating system is in charge of what the CPU is doing. Only the operating system is in charge of that. You cannot write a program that says, I'm important, get off the processor. Okay? Now, some operating systems allow for that, at least as a suggestion, but ultimately it's the operating system's job to decide who gets moved from running to ready and ready to running. I said I'd come back to this, right? Because this seems weird. Why would the operating system ever want to move something off of running, if it's not blocked? Something more important than ready. We call this a processor's priority. And generally speaking, real-time processes have a higher priority, right? Because if you're talking to your mom on Skype and you're also programming, okay, you're just sitting there with an open program up. There's no reason why that open program, even if you hit the compile button, why that IDE should run long enough to make your mom lock up through the stream, through Skype or Google Hangout or whatever, right? So some things have a higher process than other things. The other thing is, if only one program is running all the time, okay, then you lose the what's the word I'm looking for? You lose the sense that multiple programs are running at once if only one is ever running, right? If only one runs forever, okay? So the process of deciding who from ready goes first, who has the highest priority, and the process of when things from running move to ready is called OS scheduling. That is another job that the operating system is in charge of. It's in charge of scheduling these transitions. In fact, there's a part of the OS called the, you'll never guess it, scheduler. Okay?
That's from ready running.
So the operating system is not in charge of who is blocked. Who am I talking to, by the way? Okay, so the operating system is not in charge of who is blocked. Fate determines who gets blocked. Fate and what the program needs to do, what other programs have been doing and need to do. You know, like the state of the system determines if I'm blocked or not, right? Because it just means I'm waiting on a resource. If I start to wait on a resource, I always move to blocked. And if that resource becomes available to me and I can claim it, I always move to ready, right? And the operating system always does that, at least in this model.
All right, is OS scheduling, is that moving from running to ready or from ready to running?
Both.
Okay.
Yeah, both. Because both of those matter, right? There's nothing that says that just because I've been ready for longest, I get to go first. And certainly, if a decision needs to be made to move a running process off the processor, and that's certainly something only the operating system has the authority to do. Okay? All right, other questions? That's a good question. Thank you for asking that. Other questions? Okay, so how does this happen? This is called, the nitty-gritty details of this are called context switching, right? Every time a running process stops executing, right? So when a running process transitions off the running state, okay, then the OS saves all information about that process. Effectively, what you do is you store the current state of the PCB, process control block. Throw something, no. Process control block. Yeah. So it just goes whizzing by my head, I don't know. Yeah, there you go. Okay, so let me say this again because it doesn't do any good. My handwriting is so terrible. This is called context switching. When the running process transitions off the processor, the OS saves all information about that process. Okay? In other words, you have to store the current state of the PCB, process control block. Because it needs to be seamless from the perspective of the process itself. Okay? The process lives in a world where there is one process and one processor, and always they are together. The operating system knows that that's not the case, but the process doesn't. Okay? The program gets to pretend like it has sole use of the CPU. Okay? That's why, right? When we break it down, that reason is why we want processes. Okay? One, it supports the abstraction of one process to one CPU. That's not true. CPU is busy. It's got lots of clients, right? But as far as the process is concerned, the CPU is only available to it. It's the only process in the whole world. Okay, as far as it's concerned, on the whole computer. Secondly, there's a neat thing that comes out from the other end as well. So this is one possibility, where we've got a CPU, and that CPU talks to a single process. Okay? Well, that's the processor worldview. We know that. Also, you could say, hey, this CPU has multiple processes. Okay? All right, well, at the very least, this is true. Okay, it's talking to multiple processes. But each of these processes is completely unaware of the other processes and completely unaware that the CPU is not solely interested in serving that process. Okay? So, what happens if the CPU changes? Either the hardware gets updated, or we have multiple CPUs. And you might even say multiple cores. Okay? All right, so because we have processes, and because they already get to act like they are one-to-one with the CPU, we can build computers so that we can build an architecture so that actually this is the case. Process 1, process 2, process 3. There's a virtual CPU that gets this guy, and maybe it also takes this one. And then there's a virtual CPU that takes this guy. And these virtual CPUs, which are defined in software, are then aware that there is a CPU down here, or maybe multiple CPUs. Okay, so instead of this, we could also do this, right? CPU 1, okay, CPU 2. Okay? And more importantly, this from this point down can change without having to rebuild or recompile the processes. Okay? All we need is these virtual CPUs to take up the slack, right? They need to be aware that what the actual facts of the matter, what the actual ground truth is about the CPUs, okay? But the processes don't. Okay? So that's another thing that we get when we use processes. That's another benefit to using processes. Kind of already mentioned this. Each process can be designed and with multiple. Each application can be designed with multiple processes. The reason you want to do that is because it'll save you time. If you're careful, you can run and examine each process in isolation. If you have multiple CPUs, you can have a CPU that is in charge of running each part of your program so that they'll finish in parallel, is what we call that. Okay, so it's not strictly a one-to-one relationship or a one-to-many relationship between programs and processes. All right, I pulled this up so I could show you. So 2.3 goes into some detail. Yep, this table right here. Table 2.3.1, right, is a generic PCB of process P. So here's how everything is. Here's the things that are stored in the process control block. You got your CPU state. Okay, tells me if I'm stopped. The current state of the CPU, consisting of various hardware registers and flags, is saved in this field. Okay, so if I move to blocked or to ready, then information about the current state of the onboard registers for the CPU is stored here. Process state tells me what my current state is, running, ready, or blocked. Oh, and I moved away. I meant to tell you, running, ready, blocked is the fundamental three, is like the fundamental triangle. But one of the things that makes operating systems different is that sometimes there are other states that can be thrown in there. And I didn't want to go into detail about that in class because we're going to run out of time anyway. But you should look at that and pay attention to that in your reading. Memory assigned to P, right? So it could be a field would point to a contiguous area of main memory. It could be virtual memory. That's a thing you don't have a framework for understanding, but maybe you get the idea of it, and we'll talk more about virtual memory later on in the semester. Information about scheduling, information about CPU time and memory used, a list of open files that are associated with this process, some other resources such as printers, some way to keep track of what resources are there, who my parent is. So remember, when you fork a new process, you get the notion that the forking process is the parent and the new process is the child. Okay, so who my parent is, right? Children, a child process. C of P is a process created by P. Process P is C's parent. The identity of every child process C of P is recorded in the children field. Okay, so because that information gets saved, it's possible to program the processes to decide, am I the parent or am I the child? Okay, based on their process ID. And if you're the child, then you do something different than what the parent is currently doing. Okay. And then finally, this guy. So I said it was a data structure, and we've talked about it in general terms so far, but the data structure here makes a difference, right? Here's the CPU state is a set of integers. Scheduling information, set of integers. Account information, set of integers. What specific data structure you use to store those sets of information, right? Is it a queue? Is it some kind of linked list? Is it, what is it, right? That makes a difference in the efficiency of your operating system. Process state is just an integer or a character, some flag that says this is the state I currently am in. You have pointers to locations in memory, okay? Pointer to some index, right? That tells me, hey, this is the PCB of my parent, okay? And then things get really interesting down here when you have open files and other resources, and also the children that you have, okay? Because one way to do this, one way to implement this, and this is what's actually shown in this diagram. Okay. One way to implement this is as an array of structures. Let's look at the children list specifically. So the data structure I could use is an array of PCBs, okay, for my children, right? An array of structures. So I could have, like, in C++ language, I could have like a struct that defines what a PCB is, and I could have an array of those structs. The other way to do this is as a linked list, maybe of pointers to PCBs, okay? And this is just a good opportunity to talk about some of the trade-offs that come with your design, okay? And you don't have to be a 400, you don't have to be a senior, a junior, or a senior to understand this, okay? What are the trade-offs of an array versus the trade-offs of a linked list implementation?
Array has a fixed size.
Okay, so there's a fixed size. Why? What rule about arrays makes them always have a fixed size? Well, that's what a fixed size, that's, yeah.
We need to preserve so much
Why? Oh, consecutive memory. Yes, that is correct. Because they have to be stored in consecutive memory. Otherwise, we can't use the index, right? Because the name of the array, this is programming level again. But the pointer to the array points to the first memory address. So how do you get down to the third element in the array? Skip down 0, 1, 2, right? That many spaces in memory, and then you found the third element. If something was in between in there, it would screw up our accounting, okay? So they have to be contiguous, so they have to have a fixed size, right? But there's no wasted effort in doing dynamic allocation, right? When you start doing dynamic allocation of space, right, then you have to have extra overhead for remembering things that don't have a name, pointers to places, okay? Where things are, right? The opposite is true with linked lists. With linked lists, you don't have a fixed size, but there is the extra overhead of dynamic allocation. So I'm gonna contradict what I'm about to say in just a second, but you need to choose your poison between these two. Right? Which one do you want to have? You can say, well, it's fixed size, but I can always increase and decrease the size by copying the elements out of one array into another. But of course, the problem with that is you either always have too little space or way too much space. And if you're constantly having too little space and having to copy things into bigger arrays, right? How much bigger should your array be? Should you make it twice as big? Because if you do that, then it's likely that you're not going to fill up that array for a long time, maybe ever, and you're going to be wasting space. Should you make it one element bigger? Well, what happens if you have to add a bunch of new processes and then you're having to copy everything into one that's bigger? That fills up. You have to copy everything into one that's bigger. That fills up. You have to copy everything into one that's bigger. That fills up. Okay? That's a drawback, but you don't have to worry about dynamic allocation. Now, the one I said I was going to contradict that statement that you have to choose between these two. There is, and your book spend some time going over this, and again, I'm gonna have you read that. There is what's called a listless implementation. Still has some drawbacks, but it doesn't maintain a linked list. It just lets all the PCBs point to each other in a predetermined way, right, to maintain the structure of child and parent. Okay? So we also need to have what's called a waiting list and a ready list. The waiting list are the PCBs for all processes who are blocked. And the ready list are pointers or copies of, depending on how you want to implement it, PCB for all processes who are ready. Why is there not a need for a running list? Only one thing at a time can be running. Okay, so we don't need to keep a track of that. So if we combine the waiting list in union with the ready list in union with the one running process, then altogether that's all the processes that are in our system. Okay? All right, any questions? Okay, then I'm done. read if you haven't already, and do I think there are actually some challenge activities as well as participation activities for sections 2.1 through 2.3 in the Zybook. You're required to do all of those. The exercises at the end are not assigned because you don't submit them via Zybooks. So skip those. I'm not doing any of those yet. There may come a time when I assign some of those as like an exercise, but don't get confused. I called your homework exercises in the syllabus. That's not the same thing as the exercises that are at the end of each chapter or each section. Okay? Does that make sense? Also, there will be another homework, exercise number 2, where we start to build our own shell implementation. We're going to do some fundamental things to try and bootstrap into eventually building our own simple shell. And it's going to require you to have access to the server and to be comfortable, at least to some degree, accessing that and working on files on the server. Okay? So if you, and I don't think anyone did, but if you completely had an awful time using the server and you never figured it out, this last exercise, you need to get that figured out, because we're not going to leave that for a few exercises yet. Okay? All right, I'm done. I'll see you guys next week. Oh, and that's going to come out probably tomorrow or Wednesday, so be looking at Canvas for that.